the speaker is Dr. Derek Hengeveld, and there was a co-speaker, Mr. Jacob Moulton. They were both talking about the Veritrek. Dr. Hengeveld is the technical lead for Veritrek and have conducted progressive research in the area of reduced order modeling for over 10 years. His research interests include advanced modeling and the numerical methods as applied to thermal systems. Result of direct work have been successfully transitioned to application within Department of Defense, NASA, and the HAVEX industry. And Mr. Moulton is the Veritrek expert who has been assisting thermal analysis daily to improve their models, incorporate reduced order modeling into their workflows, and understand Veritrek results. During his career, he has worked on designing, developing, and analyzing and testing thermal control hardware for a broad range of applications. The thermal analysis and design is very, very crucial for aerospace. They will use a very exciting example today, the Mars helicopter with Mars 2020, which will be landing pretty soon around February 15 or 18. Next Saturday, we have a speaker talking about specifically on Mars 2020, but today, those two, Dr. Hengeveld will talk about this as an example for their analysis. So let's welcome Dr. Hengeveld and Mr. Moulton. Thank you.
Yeah, thank you. Can we give Jacob the control so he can screen share? Awesome. Yeah, this is Derek Hengeveld. Really appreciate the time to be here. Also, Jake, he's going to be talking a little bit. And so, as Ken had mentioned, we're going to be here talking about Veritrek. And essentially what it is it's a reduced order thermal modeling tool, specifically for the spacecraft community. So both Jake and I, we primarily work with spacecraft thermal management, spacecraft thermal engineering. And so most of the examples and most of the work here is kind of in that area. Veritrek kind of got it started about 10 years ago. I was doing some work with the Air Force Research Lab, and at that point, they were in the working on the responsive space effort. If you're not familiar with that, typical spacecraft might take years to develop. And the Air Force was looking at, hey, can we try to do that in 6 days? From mission call up to launch, trying to do that in 6 days. So with those condensed timelines, one area that they were looking at is how can we speed up thermal analysis? And so I started developing, this method that, eventually became Veritrek, of looking at that. And so, so I'm going to talk about Veritrek. Jake's going to give some examples of what it looks like. And then we're also going to talk a little bit about our work with Mars 2020 helicopter, which, Ken had mentioned. It's pretty exciting. It's going to be landing here soon. We've used Veritrek in a number of ways for that effort. We can see the video of what that looks like here. All right, Jake, we can move to the next slide. So we're both Jake and I, we're part of a load path, which is used to be a small business, about 25 people. We're based out of Albuquerque. We do a lot of work with the Air Force Research Lab. We do thermal engineering, thermal analysis. We also do a lot of other things: mechanical design, structural testing, deployable structures. You can see some examples here. Done some work on the ROSA, which is a rollout solar array, SSOA, which is a space flight rideshare mission. I think it had maybe around 50 or 60 payloads that launched on that mission. And then another one that recently came back down, we did some work with Assets 2, which is an oscillating heat pipe experiment that flew on the X-37B for a couple of years. And it's been pretty fun because we actually got the hardware back and we're just looking at that now. I wanted, I said earlier that, we used to be a small business. We recently got acquired by Redwire. And so you'll see some Redwire notations throughout. So just a quick, kind of a background of, the business that we're a part of. Okay, so from here on out, we'll be talking Veritrek and Mars 2020. I do want to mention, though, that if you do have any questions as we go through, feel free to type them in the Q&A or, raise a hand or whatever. I'd like to make this fairly, make this more of a discussion. So if you do have questions, feel free to just type those in and we'll try to answer those as we go along. All right, Jake, we can move on. Okay, so what is Veritrek? As I mentioned, we work in the world of spacecraft thermal engineering. One of the more predominant thermal analysis tools in that area is called Thermal Desktop. So a lot of the examples that we're going to provide are, based on Thermal Desktop. So basically what Veritrek does, it takes your high fidelity thermal model, again, in this case, Thermal Desktop model. It could be thousands of nodes. In the spacecraft world, we're dealing with conduction and radiation typically, don't typically deal with convection. And so you have this high fidelity model that includes thermophysical and optical properties. It could be multi-thousand nodes. We take Veritrek, which consists of two components. The first one is a creation tool, which basically puts its hooks into your high fidelity model, and it converts that model into a reduced order form. And we'll talk a bit about what that means. Once you have the reduced order model, then you can run that reduced order model. And really the advantage, typical thermal analysis for spacecraft can take minutes to hours to days to run a single simulation. Once you convert it to a reduced order model, you can run thousands of simulations in seconds. So, that's kind of the advantage here. We're trying to run simulations very quickly, which opens up our analysis space. All right, Jake, do you have a quick video to just kind of show kind of the end result of all of this? So this is an example of after the process of creating a reduced order model. This one happens to be a reduced order model created for the NASA Crew Exploration Vehicle, which was a fluid-based system consisting of different working fluids that they were trying to evaluate, and it had a regenerator and a radiator. Essentially what's happening is that the user is changing input factors here in the middle section. You can see that we're changing slider values. And what's going on the right-hand side is the response to those changes in input factors is changing this response surface. And I think the take home here is that every time we're moving a slider, we're basically running 400 simulations to generate this response surface, to look at the relationship between inputs and outputs. If you wanted to do that in a traditional spacecraft thermal analysis sense, it'd just be too cost prohibitive. You have 400 simulations. It takes minutes, maybe hours. I think that particular model probably took about 30 to 45 minutes to run a single simulation. It could take you a week to generate a single response surface. But by first converting it to a reduced order form, we can generate those response surfaces, in near real time. All right, Jake, we can move on. All right, so here's just a quick rundown of what a reduced order model is, from our point of view. In some cases, folks, they take, 1,000 node, multi-thousand node models, and they reduce node count. That's not what we're doing here. What we're doing is we're sampling and data fitting. It's actually, when you break it down, when you boil it down, it's a fairly straightforward process. And so let's say we have a thermal model that we built up, high fidelity thermal model. And let's say we have a heat load in that thermal model, and we want to look and we want to track, let's say, a temperature response as a function of that heat load. Well, we'd simply just adjust that heat load. We'd vary it from a low value to a high value. And here, this is our input factor. And so we run that heat load at 0 up to 5, let's just say watts. And then we're going to track the temperature output response. And so we run the simulation 6 times. We generate these red circles, which we would call training data, and we see how that output response responds to that change in input. Well, once we generate that training data, what we do is we do a data fit. In this case, the data looks fairly linear, and so we put a linear fit to it, come up with this equation y equals 10x plus 10. And so then down the road, if someone would ask us, what is the temperature at, let's say, an input factor of, let's say, 3.5 watts. Well, we could go back to the fundamental thermal model, but that's computationally expensive. It's going to take, again, minutes to hours to days to run. Why not just use the model that we just generated? So put in 3.5 into the equation, and out comes our output response of 45. And that's essentially what we're doing with Veritrek. We're generating training data and then doing a data fit. Except with Veritrek, we're expanding it quite a bit, as you saw in the previous video. We have multiple input factors, multiple output responses, and then the brains of Veritrek is, we're doing intelligent sampling, and we're doing robust data fitting. So typically with spacecraft components, and since we're dealing with a radiative environment, kind of a T to the 4th relationship, we have a lot of non-linearities, and so we need a robust data fitting scheme that can handle data that isn't always going to be so nice looking as what we see here. All right, Jake, we can move on. Okay, so why Veritrek? Hopefully started to see, and I would say, even beyond just why Veritrek, why reduced order modeling? We have our high fidelity model, which we see in the upper left. Those are powerful modeling tools. I'm assuming a lot of you folks are using high fidelity simulations. And they're very capable. They can do a lot. The challenge, though, is that it can take a long time to run a single simulation. And that's the big ask, right? That's the big sacrifice. And so with Veritrek, if we can convert that into a reduced order model, we can get thousands of simulations in seconds. And so by doing that, we can expand the type of analysis that we do. We show some examples of different analyses that we can do within our framework. We have optimization studies, sensitivity studies. We're just coming out with a model correlation feature that allows you to rapidly and more confidently correlate thermal models. And then we saw some other things like the response surface and kind of the typical things like the 2D factor sweeps and point analysis. So essentially by converting to a reduced order model first, we can run many more simulations, gives us expanded analysis capabilities, and then improved understanding. Hopefully we'll see some of those examples when we talk about Mars 2020. All right, Jake. Okay, so as we've been talking to people about using a reduced order modeling tool set, initially we thought, well, this would be a great tool kind of early in the design stage. We want to do trades. We want to look at different, maybe different thermal management options and compare those. But as we've talked to people, we've learned that they're really using reduced order modeling throughout the design life cycle. So not just early in the design stages, but also when you have a detailed design and you want to look at, let's say, thermal design sensitivities. And then during model correlation, when you're starting to do TVAC testing, we can use reduced order modeling to help with that. And then also later in the design life cycle during mission ops, and we'll see that example with Mars 2020. In fact, Veritrek and reduced order modeling is going to be a component of the Mars 2020 mission ops planning here in a couple weeks. So we're excited to be a part of that. All right, next slide. All right, so I'm going to turn it over to Jake. He's going to kind of give you a little demo of our approach on reduced order modeling, and then we'll talk Mars 2020. And again, if you have any questions, feel free to type those in.
Yeah, thanks, Derek. So these next couple of slides, I'm just going to talk about some more of the details involved with how to use the Veritrek software. I'm going to start with how we build a reduced order model using the Veritrek creation tool. I'm not going to get into too many details here with the thermal desktop interaction. Certainly, if there's any thermal desktop users out there, feel free to reach out to us. We can do a more personalized and detailed demo of the creation tool with you, kind of talk about your thermal desktop models. But for now, just kind of keep it at a high level. How the creation tool works, it works in combination with thermal desktop. So the first thing it's going to do is just import the necessary thermal model characteristics that we need to set up the inputs and output responses of our reduced order model. From there, Veritrek will create the necessary training data that Derek talked a little bit about. Each one of the training data points, Veritrek passes off to thermal desktop where it gets performed with the high fidelity thermal model. And that happens a number of times. And so I think it's important to point out, with Veritrek and with reduced order modeling, kind of the biggest sacrifice or the biggest time investment is generating the training data so that we get an accurate reduced order model. So that's kind of the biggest time investment from the user's perspective, is just generating the training data, because again, that comes from the high fidelity thermal model runs. However, once the training data is generated, you can leverage the power of the reduced order model to do rapid thermal analysis, do a lot very, very quickly. And so once the training data is generated within Veritrek, we use our robust data fitting algorithm to complete the reduced order model creation. And then we also have a ROM testing step within the software as well to give users a sense of the accuracy and performance of the reduced order model. So we do a direct comparison with the high fidelity thermal model results and the ROM predictions to make sure that the ROM that we create is accurate. Okay, so once we create the reduced order model, it's as simple as importing that into the Veritrek exploration tool to perform our rapid thermal analyses using any of the 6 analysis features that we provide and that Derek talked a little bit about. Derek's going to go over what some of those analysis results look like for Mars 2020 specifically, but I just wanted to highlight some other work that our customers are doing and kind of how they're using Veritrek and reduced order modeling with their thermal analysis. So starting in the bottom left, the thermal team at NASA Marshall Space Flight Center is using Veritrek with some of their lunar lander thermal models. One thing that they were doing, they were specifically interested in understanding the sensitivity of a heat load going into a cryo tank as one of their lunar lander systems. And so they used Veritrek's surface plot analysis that we took a look at a few slides ago to really understand how changes in their inputs, how that affects that heat load going into the cryo tank. So they walked away with a much better understanding of how sensitive that heat load is to variations in the environmental parameters. Engineers at AIAA Engineering used Veritrek for some design optimization efforts with one of their 6U smallsat buses. Specifically, they were looking to optimize a body-mounted radiator design. So they had, I believe it was 6 different body-mounted radiators on 5 different sides of this smallsat bus, and they wanted to optimize the size of each one of those radiators to meet maximum temperature requirements in hot conditions, and then heater energy requirements in cold conditions. So kind of a balancing act there, needed to optimize the size of their body-mounted radiators for hot and cold conditions. And then on the right-hand side, thermal engineers at Sierra Nevada Corporation have used Veritrek as part of some design verification efforts with their Dream Chaser cargo model. Since this Dream Chaser cargo module docks to the ISS, they have to verify that their thermal design meets requirements in hundreds of different scenarios. And typically that would take them, several weeks or months to kind of vet their thermal design and prove that it meets requirements in those hundreds of scenarios. And they were able to kind of drastically speed that process up using Veritrek and a reduced order model version of their thermal model. So now I'm going to bring up a couple-minute demo video to kind of show what the exploration tool looks like and some of the other analysis features that we provide, kind of set the stage a little bit for some more of the detailed discussion that Derek will have here in a couple minutes with the Mars 2020 results specifically. So going to open up the Veritrek exploration tool here. At this point, we've already created our reduced order model. And so the first step that we're going to do is just import that reduced order model into the Veritrek exploration tool. Once we do that, we're going to start a new exploration tool analysis session. We'll be prompted to give our session a name, and then we're going to tie this analysis session to a specific reduced order model. So you can see we have a lot of models imported here already. We're going to choose one specifically. And now we can start our rapid thermal analysis using our reduced order model. So the rest of this video is just going to highlight the different analysis features that we provide. This first one is our point analysis feature, which is essentially an Excel-like table that's used to evaluate discrete point designs. So you can adjust thermal model parameters on the left, different heat load values, and we can see output responses on the right-hand side update in real time. Next, we're going to look at our factor sweep analysis, which is essentially a 2D parametric sweep plotter. So we're sweeping through different values of an input parameter on the x-axis and looking at how an output response on the y-axis changes as that input parameter varies. And again, we can make adjustments to other thermal design parameters on the left, and we see our output response update in real time on the right-hand side. Next, we're going to look at our surface plot analysis feature, which is an extension of our 2D parametric sweep plotter, but we're actually sweeping through different values of 2 input parameters on the X and Y axis and looking at how an output response on the Z axis changes. And so again, leveraging the power of the reduced order model, we can change design parameters on the left-hand side and see our outputs update very, very quickly on the right-hand side. Next, we're going to look at our screening analysis feature, which essentially allows us to understand the relative impact that each input parameter has on an output response. So we can use this analysis feature to really understand which parameters of our design are driving our mass, which parameters are driving our cost, which of our thermal design parameters have the biggest impact on maximum temperature of one of our components. So that's really how our users are using this screening analysis feature. Next, we're going to look at our optimization analysis feature, which is essentially a dot plotter that allows us to visualize our design envelopes. And so what I'm going to do in this example is just compare 2 different designs side by side. So one will be kind of a nominal thermal design for a small satellite. And then the second design that I'm going to set up is leveraging some of our load path thermal control hardware products. We're going to switch over to a deployable radiator and put a thermal energy storage panel on our payload. And so what we're able to do with this analysis feature is very, very quickly interrogate each of these 2 designs with thousands of points. And we can see that with our load path design, we're able to reduce the maximum temperature that our payload sees by about 15 degrees Celsius. So, can perform design trade-offs very, very quickly with that optimization analysis feature. And lastly, a new analysis feature for us that we just released commercially this week is our correlation analysis feature that was developed to assist teams in correlating their thermal models to thermal test data that they actually measure in their lab. And so how this analysis feature works, we put the values that we want to correlate our thermal model to here in the experimental output section. So this would actually be our thermal test data, the data from the thermocouples that we obtain from our thermal test. So we specify the values we want to correlate to, we give a margin criteria, and then we can use the power of Veritrek and the reduced order model to have Veritrek tell us which combinations of input parameter settings effectively correlate our thermal model to our thermal test data. And so this list on the right-hand side, each one of these rows is a different combination of input parameter values that effectively correlate our model to the test data values that we want. Okay, and so I'm going to jump back into the slides here. And I just want to talk a little bit more about that model correlation feature that we just looked at. Again, that's a new feature for us that we just released in Veritrek version 4.0 this week. And it's really a new approach to the model correlation process. Typically, when engineering and design teams are correlating models to test data, you have some uncertain input parameters that you're comfortable with varying, and you want the output results of your thermal model to line up with the data that you actually measured in your thermal test or in the lab. And typically it's, kind of an iterative or manual approach of tweaking some of your input parameter settings, looking at the output results and seeing if they line up close enough with the thermal test data. And that's really why Veritrek can be, and this new analysis feature can be so powerful, is we can leverage the power of the reduced order model to modify those parameters and perform that comparison very quickly. And in fact, we can do that comparison thousands of times. And the end result is Veritrek providing us with multiple solutions that effectively correlate our model to test data. We've had great response and feedback from beta testers. You know, we're really excited to bring this to our customers and bring it to the market. You know, the feedback that we've heard so far is it's just a more confident approach to the model correlation process. There's multiple solutions out there that Veritrek finds, and it's an automated and repeatable approach. We do have some, you know, I just want to take a few seconds to point out, with this new release of Veritrek, we do have some webinars coming up that you can sign up for on our website if you're interested. We'll go into a lot more detail about this model correlation feature, along with some of the other user-driven capabilities and improvements that we've made with our latest Veritrek release. Okay, and with that, I'll turn it back over to Derek, who's going to talk in some more detail about the Mars 2020 helicopter and how the engineering team at JPL used Veritrek to assist with that effort.
Yeah, thanks, Jake. Yeah, so the Mars 2020 helicopter, if you're not familiar, it's part of a mission that's going to be landing here on Mars here in a couple weeks, February 18th. There's a rover. I think on the belly of the rover is the Mars helicopter. You know, we saw a video of what that looks like flying around. Essentially, the helicopter is about 1.8 kilograms, you know, solar powered, wireless communication, has, you know, counter rotating blades, you know, has the typical components, you know, computers, nav sensors, cameras. Basically, it's going to go out for short flights. It's going to, you know, take some images and then come back to the rover. Essentially, from the thermal perspective, you know, solar power charges the batteries. Of course, we need the battery energy to run things, and then internal heaters maintain operational temperatures. One of the big challenges is keeping the helicopter warm enough, and so Veritrek helped out with, you know, evaluating that. And so there's really two ways that Veritrek helped out. One is with the thermal design, and then another is upcoming is with mission ops challenges. Next slide. Okay, so on the thermal design side, this was a couple years ago. We started working with JPL. You know, they were developing the thermal design for the Mars helicopter. You can see the thermal desktop model in the upper right. Again, a high fidelity model. They had many challenges. You know, it's mass constrained. You know, it's a little under 2 kilograms. You know, and that's hard for thermal. It's power constrained. You know, it's picks up energy from solar energy, stores it in a battery. You know, we don't have unlimited resources there. Also volume constrained, and it's going to be autonomous. You know, it's going to receive some commands, and it's going to go out doing an autonomous mission. So a lot of challenges there from a thermal perspective. And so when they were doing the design, what they wanted to look at is exploring the sensitivities of thermal drivers. You know, how did different thermal design components, how did those things impact things like battery survival energy? And then also they wanted to use a tool to be able to do some sort of final assessment of the thermal design. And so we created a reduced order model, you know, a couple of years ago, had 6 uncertain input factors, things like environmental convective environments, so wind speed and heat transfer coefficient, some uncertainty in the applied heat loads, gas gaps within the fuselage, so, you know, tiny gas gaps that potentially could be more or less insulating, cable wire conductivity, fastener bonding conductance. These are all things that are fairly uncertain when you're doing thermal design. You can get some handbook value, but you know, there's some uncertainty involved in that. And then also battery heater set point. You know, how are the battery heaters going to be operated? At what temperatures are they going to be operated? And so we use those uncertain input factors to generate a reduced order model, and we tracked 36 output responses. And essentially those output responses were things like component temperatures, and then also energy requirements. So an example would be battery heater survival energy. All right, next slide. All right, and so here's the results of that work on, you know, evaluating the thermal design. We generated the reduced order model. We tested that model. We can see some of the test results in the upper right. You know, working with JPL, they deemed it, you know, accurate enough. Essentially, what we're seeing in the upper right are test results that compare thermal desktop, what we would call truth results, against reduced order model prediction results. We'd like to see all these red test dots fall on a 45-degree line. You know, there is some noise and some scatter, and it's really up to the end user to determine whether that's acceptable or not. And so we determined that that was, you know, good enough. And we basically did those two things that I mentioned before. One is we did a checkout of the thermal performance of the design. Does it meet all the requirements, or basically does it fall within the design envelope? An example is in the lower left. We used our optimization study to evaluate, you know, a number of different output responses to ensure that they met the requirements. An example in the lower left shows that it doesn't. In this particular example, we can see some of the outputs, they're falling in the keep out zone. And so they had gone back and they had refined the design to ensure that all the points fell within the keep out zone. So just an example of, you know, way we use reduced order modeling. That particular plot in the lower left is probably, you know, on the order of maybe 1,000 points that we can quickly run just in a few seconds to evaluate that. Even more interesting is the plot in the lower right. We used a sensitivity study to look at those relationships between input factors and output responses. And so in this plot in the lower right, we're looking at sensitivity of input factors and how they impact survival energy of the battery. You know, how much energy do we need to keep the batteries and the systems warm enough so we can fly the helicopter? And what the JPL wanted to determine is, of those input factors, which are the leading culprits that impact survival energy? You know, is it a cable conductivity? Is it a battery set point? Is it a gas gap? And by using this sensitivity study, the longer the bars, the more of an impact that they have on the output response. They found that, you know, gas gaps was a big driver, but that is a design change. But secondarily, just something as simple as adjusting the battery set point had a huge impact on survival energy requirements. And that's much easier for them to adjust. And so they went back to their design and they adjusted the battery set point to, you know, to minimize the required survival energy. So again, just a quick example of, you know, how Veritrek or reduced order modeling was used to evaluate the design. You know, we looked at design envelope and we also looked at thermal sensitivities. You know, in talking to JPL, this is an effort that probably would have taken months. You know, I think they said about 4 months, and we got that done in about 10 days using reduced order modeling. All right, next slide. Okay, before we jump into mission ops, it looks like we have a quick question. How was the propulsive thrust determined for the helicopter to hover over the surface? And what RPM does it require? I don't know, and I don't know. Unfortunately, I don't know answers to either of those. I apologize for that. You know, that's kind of got, we'd have to pull in some of the JPL engineers for that. I know it's a very challenging environment. You know, the air certainly isn't as thick as it is here. Yeah, I just don't have an answer for that, so I apologize. Okay, so jumping into the second way that Veritrek's being used, you know, Mars helicopter mission ops. We can see an example of the rover and the helicopter in the upper right, and then the helicopter as they're, you know, doing some integration in the lower right. So you can see it's very small and lightweight. We talked before, the solar power charges the batteries, interior or internal heaters maintain operational temperatures during, you know, fairly cold Martian nights. And then after receiving commands from Earth, relayed through the rover, the helicopter is going to go out and fly, you know, do it autonomously and then come back to the rover without any sort of real-time input. And so the surface operations, they're really limited by a tight energy budget. You know, we have a limited battery energy supply. We're trying to keep things warm enough on these cold Martian nights, and energy is really crucial here. We want to have enough that we're going to keep things warm enough so we can fly this thing around. Also, it's time critical because of the communication window. You know, I'll show you what that looks like in a little bit. You'll see that time window. And then finally, you know, I mentioned before, it's strongly dependent on the thermal survival energy use. Again, survival energy is key. We want to keep this helicopter warm enough so that when we want to run a mission, when we want to fly it, our components are at a temperature that we can do that. Next slide. Okay, so here is an image of kind of a day in the life of the helicopter. I'm not going to go into all the details of this. Essentially, we're relaying information from Earth, out to the rover. The rover gets information and pushes that to the helicopter. The helicopter goes and does its flight. It comes back to the rover, and then the rover, through some satellite links, gets information back to Earth. The main take home here, though, is that on a daily basis, we have a very, very limited time window to get telemetry from Mars, receive that telemetry, and do something meaningful with it to plan for the next day's mission. And so there's a couple needs that JPL had. One is quick model correlation based on that telemetry. So, of course, Mars is going to have changing environmental conditions. Those changing environmental conditions changes basically the thermal performance, and we want to adjust our thermal model. We want to correlate our thermal model to that environmental telemetry. So we're basically modeling things as accurately as we can. Quick model correlation is really crucial for that. The other thing is that JPL wants to evaluate multiple scenarios of operating the helicopter. When are they going to fly it? Do they fly it an hour earlier or an hour later? What are the impacts from a thermal perspective on those adjustments in the mission profile? Also, how do we warm this helicopter up to minimize the required energy? Do we run low power heaters for a long duration, or do we run high power heaters for a short duration, or maybe a combination? Do we ramp things up, that kind of thing? So they wanted to look at multiple scenarios, but the problem here is that we had a limited time window. We had just a few hours to be able to do that every day. And so in a traditional sense, using standard thermal analysis tools, you just don't have enough time to do this effectively. So by first creating a reduced order model, we're able to overcome some of those challenges. All right, next slide.
Actually, Dr. Hengeveld, 5 minutes.
Yeah, thanks. Yep, we're just finishing up. All right, so here's some examples of the reduced order model that we put together. We had a little extra schedule to put the ROM together. So honestly, Jake had mentioned earlier that the biggest sacrifice for our approach is that you have to generate training data. As you can imagine, the more training data, the better your ROM performance is. And so we just threw a bunch of training data at this thing. We had the time, so we kept running and running and running. And we came up with a reduced order model that was very effective. You can see some examples of the test results in the right-hand side. The one on the top is for battery energy, and the one on the bottom is for upper sensor temperature. The ROM that we built had 8 input factors. Across the board, it consisted of convection conditions, battery heater set points, and different configurations. We're also tracking 19 output responses. We used 3,600 training runs and 144 test runs to really vet this thing. And then in talking to JPL about this, kind of the feedback that we got is that it considerably speeds up the model correlation parameters to receive telemetry. So what that means is that it really enables them to correlate their thermal model on a daily basis. They've used the ROM and evaluated it. Of course, they want to do some kind of dry runs before it lands. And so they're able to do daily model correlation using this approach. It also enables instant exploration of different mission scenarios. We talked about different mission times and different warm-up profiles, and so it allows them to look at those things very quickly, definitely in the time scale that they need to be able to do that. And kind of the final take home, that it's really enabled more effective and efficient daily planning and operation for the helicopter. Something that I think they were pretty nervous about trying to get done. Now with Veritrek and reduced order modeling, I think they have a lot more confidence that they'll be successful. So here in a couple of weeks, we'll hopefully get some good news from JPL and everything's working as they had hoped. Next slide. Okay, so that's all we had. I wanted to make sure we had a couple minutes just in case there are other questions. Just a couple last things. The helicopter is going to land February 18th, so keep an eye on that. I know we will. As Jake mentioned before, we have a Veritrek 4.0 release. If you're at all interested in what we're doing with Veritrek, just go to veritrek.com or email Jake or myself. We'd be happy to talk more about that. Or if you think you have know someone that might be interested, feel free to just shoot them our contact info. All right, and it looks like there are some questions from Victor. Victor, you're bringing up some good questions. Unfortunately, I just can't answer your questions today. Were you able to test in zero G? I'm not sure that they did test that in zero G. I can't say that for sure, but in talking to the thermal engineers that we worked with, I don't ever remember having that conversation where they did any sort of like zero G parabolic flight testing. So my sense is that they didn't do zero G testing. I know they probably did a representative environment or as close as they could, but under 1G gravity and conditions.
Oh, yeah, I was just looking at the picture. I thought it looks like it was being tested somewhere. It's flying. I thought maybe it was that's just a simulation then. That's not an actual
yeah, so this video I think is just a rendering of what they expect it to look like on Mars.
Okay, so let me get your system straight. So your system is for thermal management, primarily thermal optimization and thermal management of the craft itself. Is that correct? Craft system.
Yeah, the work that kind of our world is thermal management and thermal analysis. That being said, we're starting to look at how to use reduced order models beyond. You saw from the example of what we're doing. I mean, we're sampling and data fitting. So I mean, you can apply that approach to pretty much anything. Right, so structural analysis, optical analysis. In fact, we have an effort with NASA Goddard right now looking at using reduced order modeling for stop analysis, which is structural thermal optical analysis. How can you,
So you guys are new. I mean, have you had previous experience on the space program as far as thermal analysis and management from prior spacecraft, such as shuttle and whatnot?
Yeah, we do thermal analysis outside of the JPL work. We work with a number of other companies providing thermal analysis, thermal management, thermal hardware solutions. We showed some examples kind of early on. One being like the Assets 2 program, so that was an oscillating heat pipe experiment. We also done regular missions too. We have quite a bit of experience in that area.
Right.
I haven't done much shuttle work though. We've done some ISS stuff.
Yeah, spacecraft in general.
Yep, spacecraft in general. That's right. Yep. Yeah, any other questions?
Yeah, folks, this is a great opportunity. So if any question, but looks like our time is up. So our next speaker also come for JPL. So we have actually several JPL people here. So Derek, maybe you can stay around and see what they were doing. Certainly they enjoy what they're. Hey, I think there is another one, but time really up. I think Randall asked a question. Just quickly, what form of input models are used to generate ROM? Also, does the program generate models that can be incorporated in other programs? Does the program handle? Well, you can see it, right? You can see it.
Yeah. Yep. So so we're asking about input models used to generate the reduced order model. Not quite sure I understand that question. Randall, if you want to clarify a little bit, and I'd be happy to answer that. Does the program generate models that can be incorporated in other programs? Currently, no, but we have talked to a number of folks that they want to use the reduced order models in other programs. So let's say they have their own MATLAB code or Python code, or they want to port it into some other tool. So we are looking at that, what that means to us. Currently, we don't allow that, but something that we're actively looking at. And then finally, does the program handle fast transients? Currently, well, we can handle transient simulations, and we provide outputs of those transients, but we don't replicate the transient, kind of the temperature versus time profile. That being said, our approach to reduced order model could do that, and we have had talk with people using reduced order modeling for transient simulations, things like model predictive control. And so that is an area of, kind of transient simulations to help with control. That's something that we're looking at. Hopefully that answered some of those questions.
Okay, fantastic. So if any more questions, we'll forward to you. And
Yeah, great.
we also post the today's event on our newsletter website, so people welcome, see if they can contact you directly as well.
Okay, yeah, great. Yeah, well, thanks everybody. Yeah, this is fun to be a guest here. So thanks for your time.
Yeah, great pleasure. This is a very good demo. It's very exciting.
Great,
Okay,
thanks.
so thank you so much again. So our next speaker is from JPL, is Dr. Patricia Beauchamp.